for example, a green roof. A green roof is a field of plants. What do they also do? What do plants also do? They absorb particulates. That is, they adsorb particulates. They stick to the surface of plants and get washed off into the rain, which the most deadly air pollution particles are what they call the sub 2.5 micron black particulates. Those cause most of the pulmonary damage, at least in the United States and much of the world. They stick to plants very readily. So green roofs are a major support. Bringing green is a major support in cleaning air pollution. And one of the big engineering areas where we need to massively improve is that we don't calculate, or we're only now starting to calculate the engineering, the building, the social value of putting ecological processes into our infrastructure and bringing green infrastructure and biomimicry and biophilic processes in.
Welcome to the Feria TechCast. We'll bring you all things science, engineering, technology, and innovation. Today we are joined by Joshua Harrison, co-founder and chief strategy officer of Leaf Island, an award-winning green infrastructure company based in New York. He also serves as director for the Center of the Study of the Force Majeure at UC Santa Cruz. For over 3 decades, Joshua has worked at the intersection of art, ecology, and systems strategy, from designing immersive installations on ocean collapse to building regenerative models for wildfire-impacted landscapes in the American West. His current focus spans across transforming cities into functioning ecosystem using modular, scalable technologies, starting with rooftops, walls, streets, and coastlines. So, Josh, welcome to the show.
Thank you very much, Ezekiel. I'm very happy to be here.
Okay, so let's dive in. Firstly, enlighten us about your work at Leaf Island and the product GaiaSoil.
Well, thank you. Leaf Island is a company that I founded with some partners to sort of look at how we can bring basically greenery back into cities like New York, which is largely a concrete and steel city with a little bit of green space. It's about 14% park space. And what we can do to sort of help cities recover the natural functions that they need to do if we're going to live and thrive over the next few hundred years. In other words, the cities right now are, uh, and the first thing we looked at um, was the problem of heat in a city. What people here call the heat island effect, which is basically that urban areas, by and large, are hotter than the surrounding countryside by 2, 3, 4, 5, 6, even 10 degrees centigrade, depending on where and how the structures are. And most of that is about the design of the cities. And most of that design is that they fail to take into account nature's really, really powerful main tool for cooling the planet, which is the evapotranspiration of water from leaves and plants globally. It's kind of the oldest cooling technology on the planet. It's been around for hundreds of millions of years. It's been worked through in all kinds of different ways, and we've steadfastly, at least in the West, in Europe and the United States, since we discovered, the quick energy of oil, we've basically forgotten it. Lots of other parts of the world have not forgotten it. So we have to actually recover a lot of the ways that other parts of the world have never stopped behaving. They look at the sun, it's hot. They look at trees, they provide shade. They understand there's a connection between those two, and it might have to do with how you live. So we started Leaf Island in response to a competition about the heat island effect in New York. And we were asked to build a design for the food market in New York. It's a place called Hunts Point, and it's the largest food market in the United States because New York's the largest city, not surprising. And it's a series of giant warehouses, big, over 1 million square foot each. And at the same time, there's lots of truck traffic. There's a number of residential communities there that, needless to say, are not very well served by all the amount of dirt, pollution, noise, and difficulty of living next to so much activity. And we were asked to sort of come up with a strategy that might help that. And the strategy we came up with was, just as I said, to use the power of leaves. And we happened to win that competition, which was great. But before we could actually implement the design that won the award, COVID happened. And of course, it stopped everything, broke every plan, everybody left, the government changed, all plans shifted. And so we ended up with an idea that we thought we could apply elsewhere. And the really core essence of Leaf Island is, and where we got our name, is if you could take the amount of leafy green material, that is to say, complicated plant structures, they don't have to be very high, 6 or 8 inches is enough, and recovered the roofs, the sidewalls, and the streets of a city like New York to the same degree that when the first Europeans sailed up the Hudson River and the island was covered with forest and trees, but you had the same density of it. At that time, you can actually have the same ambient temperatures that exist. And you don't have to actually remove any of the existing built infrastructure to do that. You can cover a significant portion of it, and you don't have to cover all of it because New York is a vertical city. You have the walls, you have streets, you have sidewalks, sidescapes, you have all the hardscapes that we've covered with concrete and tarmac and tar as well. And you can use maybe 30% of that will get you to the density that existed prior to there being buildings there. So it's an achievable fact. And it's also much less expensive than rebuilding. And the other part about any natural system is that when you solve one problem thinking ecologically and looking at the systems of how things work, you don't just fix one problem, you address a lot of problems. For example, a green roof. A green roof is a field of plants. What do they also do? What do plants also do? They absorb particulates. That is, they adsorb particulates. They stick to the surface of plants and get washed off into the rain, which the most deadly air pollution particles are what they call the sub 2.5 micron black particulates. Those cause most of the pulmonary damage, at least in the United States and much of the world. They stick to plants very readily. So green roofs are a major support. Bringing green is a major support in cleaning air pollution. Another problem that cities around the world have, and most American cities have in particular because of the way their sewage systems were designed, is they only designed their sewage capacity to match the toilets and the sinks, and a 10% margin, which means every time it rains above a certain amount, you're over capacity for your drainage system. In New York, that amount is 0.7 of an inch in an hour, which is not that much. One heavy rainstorm for 2 hours is enough often to overload the sewage system, which means it's not cleaning your water, it's not treating your water, it's dumping it into the rivers and the oceans. So green roofs absorb water. They absorb rainwater, which is another major factor. So you can just those. And then the third one that green roofs do is they help not only by cooling the surface area, they also cool what's inside the building. So they reduce operating costs in the winter and they insulate in the summer. So they reduce heating costs in the wintertime if those are issues. So you end up with a constellation of what they call co-benefits. The term in the United States that a lot of engineers use are ecosystem services. I personally don't like that term. I don't think it's a service that the ecology does for us. I think it's a reciprocating process that we give back and it gives to us. But nonetheless, and one of the big engineering areas where we need to massively improve is that we don't calculate, or we're only now starting to calculate the engineering, the building, the social value of putting ecological processes into our infrastructure and bringing green infrastructure and biomimicry and biophilic processes in. And we've had a really difficult time figuring out what the economic value of those processes are. And that's starting to change. And that's starting to get more open. People are more open to bringing those processes in. I'll bring one more sort of large piece in, and then I'll talk about GaiaSoil for a little bit. One of the major advantages of thinking and building infrastructure, what they call blue-green infrastructure, thinking ecologically as you're designing your buildings and your living spaces, is that natural systems improve over time with maintenance. If you have a forest and you plant a forest and you care for it, it gets healthier over time. If you lay concrete, it depreciates. It has a life cycle. Now, the Romans were pretty good at it. Their life cycles are thousands of years. But most modern concrete isn't designed for the 2,000-year life of the Pantheon. So it's a depreciating asset. From the moment you build a dam, from the moment you build a road, from the moment you build anything with steel and concrete, you actually it's a clicking clock, and you can maintain it. And to some ways, you can preserve certain things for a great deal of time, but eventually they're going to fall apart and need to be replaced. So it's a depreciating asset. Green infrastructure properly maintained, blue-green infrastructure, is an appreciating asset. That is to say, it gets richer, stronger, and better over time, healthier, provides more benefits and more value, assuming that it's well cared for. And that's part of the stewardship policies that we at Leaf Island try to think about, that we're actually stewarding the planet. We're building, we're looking at ways that we enact as humans within the world that we live in ways that are not only good for us as a society, but also good for the place in which we live. So bringing trees back and landscape back also improves the biodiversity. It improves the honeybees, it improves the butterflies, it improves the various other the other things that are living in our region. And when you do that, you get all kinds of other benefits that come through. Birds are healthier. So those are sort of the principles by which we set up business. How can we look at bringing ecological services back into the urban environment? And how can we do that in ways that are economically as well as ecologically efficient and smart? And that brings us to GaiaSoil. GaiaSoil, which was invented by one of my co-founders, Dr. Paul Mankiewicz, came out of the same inspiration. He understood that if a city is going to thrive over the long term, it has to use its waste products in its ongoing existence. Just like nature has no waste. Waste is a human concept. Every output in a natural system is an input for something else. If you die, something eats you and consumes you, that brings food to something else. A plant decays into soil that helps grow other plants. Every action of life transforms itself into some other process. It isn't thrown into a garbage heap and ignored and discarded. So cities, in particular in the U.S. and in Western Europe, spend an awful lot of time and energy throwing things away. That's energy better kept inside the city, cheaper, it's better. So we, in particular, looked at styrofoam. Styrofoam is a pretty ubiquitous material. 85% of it ends up in landfills globally. It doesn't decay very well. It does and it's very light, and it's actually lighter than water, and it floats. If we took that styrofoam and put it into a artificial soil, we can actually end up with a soil that's 1/5 the weight or less of traditional soil. And even fully loaded with plants and water, it's still 1/5 the weight of traditional soil, which means it can go on as a structural additive to a lot of building morphologies without necessarily creating substantial need for structural reengineering. In fact, the carrying capacity of GaiaSoil with plants is about 22 pounds per square foot. The standard minimum roof carrying capacity in the United States by code is a minimum of 30 pounds per square foot. So even the raw numbers allow you to fit dirt. A normal soil would allow you to, would be in the order of 75 to 100 pounds per square foot in that same capacity. And the artificial soils that exist, because that's way too heavy for green roofs all over, range from 30 to 50 pounds per square foot. So we found that by using styrofoam, we were able to create this very lightweight product that also was, because of the way we create soil structure, we're able to create porosity within the soil, which allows the microbiomes and the bacteria to grow. So you end up with a bioproductivity of soil that's 150 to 170% greater than traditional soil. Not quite as good as hydroponics, but without any of the need for a clean room, without any of the need for protected infrastructure and space and careful controls, because it works functionally, biologically, just like ordinary soil. So it allows us to put green infrastructure in places where it wouldn't ordinarily be thought of. And so those are the two pieces that brought in the idea of creating, of rebuilding the natural processes that a city already has, and the concept of finding a tool that allows us to create a weight metric that's responsibly, consistently, reliably lighter, and light enough to be put in places that it can actually have the reach of a system that we're going to need. Because again, the challenge for building green roofs is one or two individual roofs are not going to make a larger difference. But if you get to 30, 40, 50% coverage, then you start to actually be in a position where you're transforming the local environment in a positive way. You're actually starting to change the temperature, not just in a micro area, but in a larger area. You can start to really change the ecology of a city, or certainly of a community within that city. So that's the basic story and process and philosophy behind Leaf Island.
That's that's wonderful. I mean, turning uh, recycled styrofoam, which happens to be one of the world's most problematic waste products, into climate solutions. That's really such an innovation that I think the world needs right now. So, Joshua, tell us, you talk about restoring the metabolism of cities. So, what does that mean, and how can a roof covered in plants help do that?
Okay. Again, I'm the idea guy in my company. I'm not the engineer, so you'll forgive me if I don't create the technical structure for what I'm saying. But I think I can communicate it. So the really important piece of all of this is that water is the primary tool by which the planet cools itself. We talk about a carbon crisis, we talk about the CO2 effect, and those are all real and very important. But the primary way the planet cools itself is through the evaporation of water, either directly off of bodies of water, like the ocean and lakes, or on land, primarily through the evapotranspiration of plants, which take in carbon dioxide, give off oxygen, and in the process, they give off water vapor. And that water vapor expands, and each cubic centimeter of water that goes from water to air is, I think, 550 calories of heat that it takes. So with a lot of plants, you basically cool a lot of area. And one of the models I'd like to talk about is if you're on the Amazon River in the middle of the largest rainforest, right by the equator. Most people who haven't lived there and haven't experienced it would imagine that it would be really, really hot. And in fact, underneath the forest canopy, and I'm sure that's true in equatorial Africa in a very similar way, in the forests, rainforests everywhere, it's actually about 85 degrees, more or less, with a constant humidity. If you go more or less to the same latitude, and you go a little further north in Africa and you get to the Sahel, where there's no plants, that same day, that same midsummer August day, where it's 85 degrees in the Amazon, it could be, I'm using Fahrenheit here, it could be 120 degrees on the surface, or even now 130 degrees, because we're getting hotter and hotter. And the difference is plants and shade. That's the power. You can either be 140 degrees in open sunlight, or you can be 85 degrees in a plant-based environment.
That is such a
So
huge temperature difference.
it really is. And that's the power that we can't, that kind of change is not going to happen magically in different places, but that's the power of the transformational possibilities. So if you think about that, and then you take, I use another story that I like to sort of share with people to give them a sense of this is, if you think about Hawaii, which is a series of volcanic islands, among the most recent volcanic islands on the planet. 1 million years ago, what's now known as the Big Island in Hawaii emerged from the ocean in gigantic volcanic eruptions. And it was bare rock for many, many thousands of years. But now, if you go to Hawaii, you think of it as a lush tropical jungle. What's that? That's how, if you think of a building like that bare rock of the Hawaiian mountain, and you realize you can cover that building with plants, and you can have that same tropical jungle effect. Again, elements of it, you're not going to get the whole thing. That's a model you can work for. And if you understand that we can assist natural processes in very real and profound ways. If you look at cities in that same way of how you assist cities to bring back those natural, one of them we already mentioned, we need to find ways to absorb our waste products. We mentioned styrofoam as one. You can also, a city like New York generates a huge amount of concrete waste and glass waste. We could be reusing that in many, many ways. Some of it we do use, we could be using all of it. If we do that, we're saving vast amounts of energy because we're not shipping it somewhere else and burying it. We're reducing our carbon load tremendously by not having to remake concrete, not having to remake glass because we're reusing it instead of remaking. If we think about New York is on a harbor, and many, many cities around the world are on harbors, and harbors are on the seaside or on near bodies of water. Those areas are enormously biologically productive. In fact, New York City was one of the great oyster estuaries in the planet. When the Europeans showed up, they could tell where the local people lived by the piles of oyster shells, which were often 10 and 12 meters high around each village. And until we destroyed that about 150 years ago through pollution and overconsumption, New York City's cheapest food was oysters. But oysters are an amazing animal, and I think they do many things. And mussels and related bivalves are similar. They feed themselves by filtering vast amounts of water. And they filter it for nutrients. And they filter it for particulates. And they filter it for all kinds of other things. In fact, a single square meter of oysters can filter as much as 2,000 gallons. So that'd be 8,000 liters a day.
Wow.
And if you imagine roughly 10 hectares of oysters, New York City has 500 miles of coastline right now because it's an island and it's irregular. And much of it is hard, it's turned into docks and hardscapes. Some of it's still groundscape and beach. But if you took 10 hectares of that 520 miles or whatever, 700 kilometers of coastline, and you spread it across maybe 3 to 5% of that, you could use between mussels and oysters, you could plant enough oysters to purify all of the wastewater. So
That's
and
that's pretty impressive.
right now, New York City is in a dilemma because they have 5 major sewage plants, and they need to build a 6th. And one of the conversations we're having is why build a 6th for their guess is $3 billion. My guess is minimum of twice that. Why not spend 5% of that money and plant another billion oysters and plant them around the outflows where the wastewater would normally go so they can capture it? And you basically need some rubble, you need to riprap, you need a certain amount of that waste, concrete and glass that we talked about, going into a design around where the sewage outflows are to slow the water down and collect the particulates. So you need a certain amount of areas to plant the oysters, and suddenly for not even really realistically 1% of the cost, let's call it 5 or 10% because, why not? You could actually replace it with a growing, self-maintaining, thriving body of seafood. Now, while you're at it, why isn't New York City growing more of its own food, both from the ocean, which is plentiful, and from all these flat roofs that could also be growing food plants? They don't just have to grow native meadow plants. They could grow anything that you want that's realistically available to them. If the roof is strong enough, you can grow trees, although that's probably not going to be very likely. So if you're thinking about food, we like to eat elements at the top of the food chain. We like to eat cows. We like to eat tuna fish and swordfish and salmon. But the top predators, well, the top predators have already consumed all the things up from the bottom, and at each time it's less efficient. Why? Because they're eating. But if you consume lower down on the food chain, if you consume much more shellfish, oysters, seaweed, you're eating things that are much closer to the original sources of production, and they're much, much, much more efficient to have a kilo of protein from an oyster is far less energy and water and all things than a kilo of protein from beef. That's even if even if it's grazing beef, as opposed to the industrially produced beef that we seem to be obsessed with here in the United States. But even if it's a much more well understood and well designed beef that's in harmony with the plant, and even presenting a situation, there's an argument for cattle being, a healthy for the landscape in appropriate numbers and appropriate density, because their hoofs and their excrement produces the kinds of proteins and filters that help landscape survive. That's fine by me. I don't have a problem with that. I just think we should be moving away from eating too much at the top of the food chain and eating a lot more at the bottom of the food chain, whether that's all plants or plants and algae, seafoods. Other countries eat insects. The United States has a trouble with that, but it's a pretty smart food source. Locusts are a very smart food source. So we have to get used to that in the United States, but I imagine that day will come. So you think about cities from the point of view of what the outputs and the inputs, creating respiratory function, if you think of plants as the lungs of a city, if you think of the waste system as the waste system of a city, if you think of these things, you start to have a sense of how a city metaphorically can be a living being, and how the community in a city, then you bring people into that. Why are people not part of this whole process? Why are the gardens not community gardens? Why doesn't every building that has the capacity have some ability to grow its own food? In the United States, a lot of people here are quite surprised when I tell them at times of emergencies, even a place as wasteful as the United States, that currently we throw away somewhere between 35 and 40% of our food that we create uneaten, which is a tragedy, a crime, and an embarrassment all in one. But nonetheless, during, for example, the Second World War, people in the United States grew 25 or 30% of their own vegetables at home. They didn't go to the supermarket. They didn't go to farms. They grew them in their own front yards and backyards. We could get a lot closer to that. And we have lots of places where they're what they call food deserts, where even though you're living in a city, because of economic and social reasons, there are very few places to get any kind of good food. In fact, the only food available often is very highly processed, what they call fast food, which is nutritionally terrible and terrible for your health and laced with chemicals. Why not grow your own food in those areas? Why not bring those capacities, and why not have people do it? Because again, we spend a lot of time protecting ourselves from living, here, where we, from living in the natural world. But for many, 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 many reasons, living in a natural world, in a more natural environment, provides, again, more of these co-benefits. People in buildings that have wood surfaces report feeling much better than people in buildings that have painted steel and artificial surfaces. People who, in fact, this is, kind of amazingly obvious, but not surprising. In many countries in the world now, not yet in the United States, but in Japan and Germany and several other European countries, and it's growing, there's a whole lot of diseases where the medical profession now recommends what they call forest bathing as part of the cure. And not just for emotional issues, but for physical issues, for respiratory issues. So that means essentially, in order to heal yourself, part of the remedy for healing yourself is spending 2 hours a day walking in the woods. Okay. People who are connected to growing their own food in a constructive way, not in a way where you're turned into a robot for an industrial farming process, but in a way where you're connected to the value and food that you're growing, report very high levels of satisfaction emotionally, physically, culturally. Why aren't we taking advantage of that? Why aren't we giving people the opportunity to own more of their own creation of food, their own creation of buildings? If they do that, then obviously we're all better connected to the world in which we live. And if we're better connected, we're better caretakers. If we're better caretakers, we're less destructive. Why would we throw things away as waste when it's our home? Why? Because we care about it. The minute we care about something, we take better care of it. Why do we have? And so all of these things, again, they're interconnected. They're the whole. And then going back to an engineering concept that I think is not as well understood as it needs to be is in a system, in an ecological system like we have, what you're really looking for is the efficiency of the system, not the efficiency of any one part. And we've often trained ourselves to look at the efficiency of a part as opposed to the efficiency of a whole. And in the efficiency of a whole, any one element of it might not have the maximum efficiency it's capable of, but globally, your aggregate of efficiency will be larger than the sum of each individual parts. And those are the solutions that we're looking at. Now, let me go to a green roof. That gets back to green roofs. So a green roof can reduce temperatures, 10 or 15 degrees. They can reduce your heating and cooling effects by as much as 20 or 30%, well designed. But green roofs also don't have to exist just as green roofs. Green roofs work very well with solar. And one of the challenges for the solar photovoltaic industry that they're finding is that silicon is set up in a factory under very carefully controlled conditions. It's temperature controlled. It's temperature controlled for a reason. Silicon reaches its maximum efficiency under factory conditions, which tend to be 70 to 75 to 80 degrees Fahrenheit. When they're put out in the world, they're often facing on a rooftop 140-degree temperatures on an unprotected roof. So if you put them into a green roof where the temperatures are already 20 to 25 degrees cooler than that, where they're providing additional shade, you're increasing the function of your solar. So solar and green roofs play extremely well together. Solar, green roofs. Now, once windmills and wind energy gets engineered to the point where small-scale modular wind can happen, wind can be part of that equation as well. Not all plants need direct sunlight, so you can have solar arrays that are raised up and shade-tolerant plants below them, and you get the effect of both. And then they're an additive effect. You could, then you can think about in a new building, you can also figure out what your design of your materials are in that building. Not all materials need to be glass and concrete and steel in the same way. Not all designs need to be, the same kind of designs we've been building skyscrapers for the last 75 or 100 years. And there's a lot of new experimentation going around. I mean, China is building cities. I think every 6 months, it seems there's another city in China that's showing different kinds of possibilities of green buildings. It's not, there's lots of places where they're really powerfully inventive things happening. And I think that one of the virtues of having global connectivity is that you can start to see things that would otherwise be harder to see. Why aren't highways right now? Mexico City has something they call the Via Verde, or the green roads. What those are is where they have a highway is a giant concrete slab. Well, when it rains, where does that water go? And pretty much it turns into water that ends up flooding under many conditions. Well, Mexico has pioneered, and now other places are taking advantage of that same idea, using plants to absorb and capture the rainwater that comes off of elevated highways in particular. And suddenly they're doing, again, they have these raised supports, these road supports that are now covered in green that are providing cooling. They're cleaning the air. They're absorbing this water that would otherwise have collected all these particulates and waste from the highway runoff, and they're storing it and eventually feeding it back into the environment. And they look good, and they're creating, so they have this aesthetic value. They have this environmental, ecological, public health value. They have this heat reduction value, and they have this water collecting value. And they're looking at existing infrastructure, and they're saying, why don't we cloak that? Most cities around the world have way too much concrete. That's another thing that could start to happen. That's another kind of technology. It's not exactly a green roof, but it's part of the green wall technology that's bringing greenery back into a city. So those are some of the things we think about. Does that address your general question, Ezekiel?
Yeah, I mean, in your attempt to answer the question I asked, you answered several other questions I wanted to ask as follow-up questions to that question. So I would say you did a pretty good job at answering that question, and you went into like great details and you were elaborate. And I really have to applaud that. So I have some few more questions since you I mean, answer some of the follow-up questions I wanted to ask. Now, tell us, how does green infrastructure appreciate in value over time, and what will change if we treated it like an asset instead of an expense?
I think that's a really great question. And it's one I've been asking for a long time. But the reason, I mean, the basic reason that green infrastructure appreciates is that its functionality, when well maintained, increases, and its longevity, let's say, the amount of time it can serve and do that function, is essentially indefinite. So that it provides increasingly effective returns. If, for example, it's water collection, if it's air pollution, if it's some of these other structural issues, if it's creating a different way of draining and water conservation inside a city or a community, it does those things not only stably, but improves them over time. That's why it becomes an appreciating asset. So its value actually increases if you think about it as the value it provides to the community under most things. A concrete, because and the biggest comparison is with concrete and steel, particularly concrete. Concrete also has to be maintained, so it's not that there's no act of maintaining it, but it has a finite life. Right now, it has, generally speaking, it has an engineered life. Concrete is designed to a 35-year lifespan, a 50-year lifespan, a 70-year lifespan. Roadways, no, they have to be replaced. Again, there are plenty of examples of people who built, like the Romans, there's still roads existing that are 2,000 years old. Okay, so you don't have to have a 70-year lifespan, but modern economics says we don't want to engineer for a 2,000-year lifespan because it would be too expensive. So at the moment that you put something in the ground, or for example, if you buy a car, the moment you take that car, that brand new car off the lot, it's already lost value. It's no longer a new car. It's now a used car. And that car value continues to decrease over a certain predicted nature. But if that actually were not a car, but were, your health, let's just make it, this is not the best example, but let's use it. But it's you walking. And as you walk, you get healthier, you get better. So the act of your walking under certain conditions, makes your body healthier. The car loses value, you actually physically gain value. I don't know that I'll use that metaphor too often, but so appreciating that. So from the largest perspective, from a global perspective about assets and building and design, the biggest challenge for us as understanding economics is that the West has imposed a certain kind of mechanistic economics, is the best way to call it, on the world which it has overseen and overwhelmed. And that's a world in which we've convinced ourselves that the primary thing we have to understand is the exact transaction that happens. I give you money for this, you give me that. We don't think about what it took to get the that. We don't think about what it took to get the money to give you this. It's just that's the transaction. So everything, for example, if you buy that car, we don't think about all the things it took to make that car happen. The land for the factory, the resources that were extracted for the steel, the pollution that came off of that, the heat that was put into the environment that helps heat the planet, the people whose lives were disrupted for the land and the places, the people whose, all of the different elements that come in, those are considered external to it. They're called externalities. And the way that economics functions, here in the United States and the way we like to see economics function everywhere, although fortunately not everywhere has absorbed this fully, is that that's all that matters. And that once in a while we accept the fact that there's a little pollution and we sort of pay to remediate, but we don't integrate the externalities into the real cost of doing business. In other words, we don't decide, is this something I want to do because I need to know how much it's really going to cost in terms of not only the specifics of the object, but all of the resources it's going to consume to make that object, and all of the impact taking those resources is going to have on the communities at large. And then what's going to happen to this object down the road? How is it going to be maintained? How's it going to be repaired? What's going to happen? So it's what some of the people here borrowing from a number of the concepts from one of the Iroquois tribes. It's called the seventh generation. So are you thinking 7 generations forward? Are you thinking 7 generations back? What's going to be the whole cost? Or as the economics they call the life cycle cost. What is the cost of everything that it took to make the item, the cost of using the item, and the cost of everything it's going to take to dispose, disperse, or whatever you're going to do when you're finished using the item. And that's the reason that appreciating assets have massive value that's not being done, because they take much more of that into account. They start to take into account externalities. They start to take into account. We don't have a way to price that yet. And, and we have a problem in Western economics about not valuing what we can't measure and not pricing what we can't measure and not valuing what we can't price. We use the term priceless in 2 ways that are completely contradictory. If it's priceless, it means it has no value. And if it's priceless, it means it's so valuable we can't figure out what to do with it. They're utterly contradictory.
Yeah.
Same word.
Yeah. Okay, that's great. I mean, that's a really wonderful perspective you put things into. So I have another question. Tell us, what's one policy change that could unlock exponential growth for nature-based urban solutions?
Um, Boy, it's an interesting phrasing, because the first thing I would say is that exponential growth is the biggest problem we face. That we don't actually understand that we live on a finite planet and you can't have exponential growth. So I understand the impact of your question. I just had to take that aside. I think we have to understand growth better. We have to understand what a regulated state looks like, where growth is controlled. But I think there's a lot of people thinking about this, and they have different answers. One answer is a realistic price on carbon, for example, a realistic measurement of what the carbon cost and carbon equivalency cost. And that price, to the extent that people price carbon now, it's, $20 or $30 a ton. It really should be 10 times that or 20 times that. And if suddenly you had to pay a carbon tax of, $300 a ton for the carbon consumed in your product, you would think about, is this the right way? You would think about more efficient ways to get the solution. Because do you need a slab of concrete, or do you need a roof? Do you need a bunch of bricks, or do you need a house? Do you need, a car, or do you need to have an efficient way to get from A to B and B to C that gets you there cheaply and effectively? And you start to think about, we don't need the objects. We need the services those objects provide. We need to live a happy life. What are the really important things? We want to have a community in which we're all living well. We want to have a life where we know we can provide for ourselves, for our family, and we know that our children will be safe. They'll grow up healthy and satisfied. They'll be able to have full, rich lives for themselves. We want to have a place where culture is available, where religion is available, where you can actually have community and be set. Those are the things we want. We don't need the objects to do that. We need the tools to give us the life that we want to live. And so so one of the simplest ways to get partway there is to start saying we're going to actually have a realistic cost for the carbon costs. Another one, which would be pretty simple, is to implement what they're starting to do in Europe, that you can't sell something unless there's a plan for what happens when its use value is over. It has to be recovered by the company that sold it, that made it. If the company that makes you something has to take it back and either turn it into something else or take it apart and rebuild it or do something else with it that continues its life cycle, then it's going to be a lot different than it is now. We need to think about ways to stop wasting food so that because we produce far more than enough protein for everybody on the planet to have far more than enough calories to live a healthy life. It's just utterly misappropriated. It's stolen from hungry people. And we give it, in the worst crime of all, we feed it we create corn in the United States with petroleum-based pesticides in order to turn it into ethanol to put it into gasoline, which as an engineering process is a lose-lose process at every step of the way. It's a guaranteed energy. We need to stop doing things like that. That's just absolutely burning energy when we don't need to do that. We need to stop feeding cows a lot of the rest of the corn and eat much less industrially produced meat, primarily cows, pork, pigs, and chickens around the world. People can certainly eat whatever they need to eat in moderation, but the food has to be produced more organic. That's 20% of the problem with the atmosphere comes from the way we produce our food, primarily the way we produce monocultures. And so these are things that once we start thinking this way, they bleed into green infrastructure. So I would say food and carbon pricing would be two of the easy fixes, and actually identify and companies being required to take care of their products. So they're able to recover all of their products and either to be repurposed, reused, or reconstructed.
That's wonderful. Wonderful, wonderful. So, I have one more question for you,
Sure.
sir. So, I normally like to save this one for the last to ask every guest I interview here on this podcast. So, tell us, what does innovation mean to you, and how does it relate to your field?
I think, that's kind of a great question. And in the sense, for me, innovation comes in many flavors. One of them, I think, is recovering things we used to know and used to be able to do and finding ways to make them real again. Finding,
Hmm.
finding ways to make them meaningful again. I think from the point of view of green infrastructure, we need to be able to see two perspectives. There's a concept that I love from a Native American tribe in the west of the United States. It's called two-eyed seeing. One eye looks at the world from a Western scientific point of view. The other eye looks at the world from an indigenous point of view. And in order to move forward, we have to be able to see both. Not because they integrate, but because they complement each other. And for me, innovation is successfully figuring out how those two things complement each other.
That's great. That's great. Wonderful. So finally, let us know, where can our listeners reach you if they want to ask questions or bring Leaf Islands solutions to their community.
Um, You can reach us through our website, which is leafisland.org. And that's probably the easiest way to get to us. We're still a pretty small company. We don't have a very big public face, but that's probably the best way to reach us. And happy to hear from people in your audience.
Great. So it's nice having you on the show today. I'm really honored to have this conversation with you.
Well, it's been fun, and I appreciate the chance to connect with you and hopefully share some of what we're thinking and doing with people in other parts of the world. That's really exciting to me. And good luck with everything.